The Challenger disaster killed 7 people in 73 seconds. That is the image burned into every American mind since January 28, 1986. But here is the thing nobody tells you. The shuttle that exploded that morning was actually flying with a known flaw, and everyone on the ground already knew about it. That sounds like the most damning sentence ever written about NASA, and it is, but it also opens a much deeper question about how space agencies define danger. Because the real risk was never the rocket. The real risk was the institution behind the rocket. We tend to picture dangerous space missions as the ones with the most dramatic objectives, the ones where astronauts land on alien surfaces, dock in the dark, or float untethered above Earth. Apollo 13 exploded an oxygen tank 200,000 miles from home and barely made it back. Columbia broke apart over Texas at Mach 18. Challenger vanished in a fireball over Florida. Those are the stories we remember because they are visible, cinematic, and final. They give danger a shape we can point to on a screen. But the most dangerous moments in space history were not always the ones that looked the most terrifying from the outside. Sometimes the most dangerous moment was a Tuesday morning meeting in a conference room in Alabama. That is where the Challenger story actually begins, not on the launch pad. In a phone call the night before launch, on the evening of January 27, 1986, engineers at Morton Thiokol, the company that manufactured the solid rocket boosters, held an emergency teleconference with NASA managers. The engineers were worried, deeply worried. The launch was scheduled for the next morning, and temperatures at Kennedy Space Center were going to drop below freezing overnight. The O-rings, the rubber seals that prevented hot gases from escaping through the booster joints, had never been tested in conditions that cold. Roger Boysterly, one of Thiokol's senior engineers, had been warning about O-ring erosion for almost a year. He had written internal memos, he had flagged the data, he had drawn charts showing the relationship between cold temperatures and seal failure. That night, he laid out the evidence as clearly as he could. His recommendation was unambiguous: do not launch. NASA managers pushed back. The launches had already been delayed multiple times. The program was under pressure. The school teacher on board, Krista McAuliffe, had been waiting weeks to go to space. One NASA manager said something that night that has been quoted in every engineering ethics textbook ever written since. He told the Thiokol engineers to take off their engineering hats and put on their management hats. That sentence is worth sitting with for a moment, because what it really meant was stop thinking about what might go wrong and start thinking about what we need to happen. The Thiokol managers overruled their own engineers. They gave NASA the go-ahead. At 11:38 in the morning on January 28, 1986, Challenger lifted off from Kennedy Space Center. The air temperature on the pad was 36 degrees Fahrenheit, the coldest launch in shuttle history. 13 seconds after liftoff, slow-motion footage would later reveal a small puff of dark smoke from the right solid rocket booster. The O-ring had failed to seal properly in the cold. For the next 59 seconds, the shuttle climbed normally. The crew had no idea what was happening below them. A flame began burning through the side of the booster and into the external fuel tank. At 73 seconds after launch, the tank failed catastrophically. The shuttle broke apart at an altitude of about 48,000 feet. The crew module remained intact for a few seconds after the breakup. Several of the crew members had activated their emergency breathing packs, which means they were alive, at least briefly. After the vehicle came apart, the module hit the ocean at roughly 200 miles per hour. Approximately 2 minutes and 45 seconds after the breakup, there was no escape system, there was no way out. 7 people died, not because space is inherently deadly. They died because one rubber seal was never tested in cold weather, and the people who knew that were told to put on a different hat. Here is why this matters far beyond Challenger. This was not a one-time failure of judgment. It was a pattern. The Rogers Commission, the presidential panel that investigated the disaster, found that NASA had known about O-ring erosion problems since 1977, 9 years before the disaster, 9 years of data, 9 years of warnings. Each time an O-ring showed erosion after a flight, engineers flagged it, and each time, managers looked at the fact that the shuttle had not exploded, declared the risk acceptable, and moved on. This is called normalization of deviance. It is the process by which a problem that should be alarming gradually becomes routine, simply because it has not caused a catastrophe yet. The shuttle flew 24 successful missions before Challenger. Every one of those missions where O-rings showed erosion but the shuttle came home safely made the next launch a little easier to approve. Success was indistinguishable from safety, and that confusion is one of the most dangerous things that can exist inside a large technical organization. Columbia in 2003 followed the exact same pattern. Engineers saw foam strike the wing on launch day, raised concerns, asked for satellite imagery to assess the damage, and were told it probably was not a problem, because foam had struck the shuttle before and it had always been fine. Sound familiar? Now put this next to Apollo 11 in 1969. 3 men, a rocket with the energy of a small nuclear weapon, and a landing on a world no human had ever touched. The risks on Apollo were extraordinary, and they were known. But they were known in a different way. They were known as genuine uncertainties, not as managed compromises. When Neil Armstrong flew the lunar module manually past a boulder field, with 25 seconds of fuel remaining, that was the frontier behaving like a frontier. Nobody had ever done it before. The danger was inherent in the act itself. When Challenger launched into 36-degree air with O-rings that had never been cold tested, that was not frontier danger. That was institutional failure, dressed up in the language of acceptable risk. The Apollo program was built by people who were terrified of what they did not know. That terror made them careful, meticulous, and honest with each other. The shuttle program, by the time Challenger launched, had accumulated enough success that it had started mistaking familiarity for safety. That is the transition that kills people in complex systems. The lesson of Challenger is not that space is dangerous. Everyone already knows that. The astronauts know it. The engineers know it. The families know it. The lesson is that danger changes shape over time inside large organizations. It starts as something everyone can see and discuss openly. Then it slowly becomes something that is documented in footnotes and talked around in meetings. Roger Boyskely testified before the Rogers Commission and told them exactly what happened. He named the managers who overruled him. He described the phone call in detail. He told them that he had done everything he could think of to stop the launch. He was largely right, and his career at Thiokol was effectively over after he told the truth. That detail should be uncomfortable, because it means the system punished the person who was most correct about the most important thing. The engineers who stayed quiet that night faced no consequences. The managers who overruled them received no sanctions. The 7 people who had no part in that phone call are the ones who paid. That asymmetry is the actual danger in complex technical systems, and it is not unique to NASA. Modern space programs have learned from Challenger and from Columbia. The investigations, the reforms, the new safety cultures, they are real and they matter. But institutional drift is not a problem you solve once and then forget about. It returns slowly, quietly, in the gap between what engineers know and what managers are willing to hear. Every complex technical organization that has ever existed has faced some version of this tension. The people closest to the hardware see things that the people managing schedules and budgets sometimes do not want to see. The question is never whether that tension exists. The question is whether the organization has built a culture where the engineer with the uncomfortable data is the most important person in the room. Challenger's real legacy is not the fireball. It is the phone call the night before and what it reveals about the distance between knowing something and acting on it. 7 people flew into the sky on a Tuesday morning in January 1986. They trusted the institution behind them to have done everything possible to bring them home. That trust was not honored, and the most dangerous thing about it was that nobody in that conference room the night before thought of themselves as the person who was going to let them down. The most dangerous missions in the history of human spaceflight were not always the ones with the most dramatic objectives. Sometimes the most dangerous mission was the one where a manager asked an engineer to put on a different hat. Apollo 11 flew into the unknown. Challenger flew into something worse, the known problem that had been reclassified as an acceptable risk. And the difference between those two kinds of danger is the most important thing any organization that does difficult work in the physical world needs to understand. Thanks for watching. See you in the next one.